All right. Today we are going to continue talking about relational algebra. By the end of today, we will know all of the basic operations in relational algebra, and um, yeah, then in subsequent classes, we're going to be trying to use these methods in order to do queries on different relations. Okay, I'll remind you that relational algebra is an algebra on relations. So relations can be thought of as tables with named columns, and these tables can have, or these relations can have entries. A single entry or a single row of the relation can be considered a point, or fine. So when we have a lot of data, we can split it up into lots of relations where this particular relation only concerns itself with a small part of the data. And then if these different relations have a relationship with one another, then we can combine these relations together and return just those entries or just those points that we care about from these collections of relations. Now, if you have more than one relation, how is it that or if you have, for example, two relations, how do you do stuff with them? That's the algebra. So relations, they can be added together. That's a union. That's when you just sort of glue the two relations together. That's a union. You can do a difference between them. So you can take one relation and you can take another relation and subtract one from the other. And then the result would be the relation minus whatever these entries are that you subtracted. So this is what's meant by relational algebra. It's a set of operations that we'll be talking about. There's 7 of them altogether, and that will be the algebra of how to add them, how to subtract them, how to multiply them, like this. Okay, so for the entries of a relation, we're considering those to be points. And so these would be points in a set. So we have to talk some about sets. Here, for notation, we use the capital letter omega for the set of all things, or quote unquote, the world. Everything that can be is inside of omega. Everything else are subsets of omega. Sets are delineated with curly brackets, and the elements are separated by commas. Sets can have a size. That's how many elements are inside of them. Some sets can be subsets of other sets. That means if you have a big set, you can also have little sets that are contained inside of the larger set. You can have sets that are disjoint, meaning no elements in one set exist in another set. Like all of their elements are unique. If that's the case, then they're disjoint. Okay. Yeah, let me give myself some more room here. So these first three set operations, they're also operations in relational algebra. Again, there's going to be 7 altogether, but these are the first 3 that we'll be talking about: the union, the intersection, and the set difference. Okay, the union of two sets, A and B, is written like this. That's the union. So A union B, and I'm going to introduce some more notation. Okay. So what this is saying is A union B is, first of all, it's a set. We know it's a set because it's in these curly brackets. So this means the set of all x, and then this line means such that. So the way that this is read is that A union B is the set of all x such that x is in A or x is in B. So this is a concise way of writing that. Give myself one here. All right. Sort of pictorially, if you have some set A and some set B, then their union is the element that's in either A or B. Do you have a question?
Yeah, real quick. What did it stand for again? Like the signs. Can you just repeat that one more time?
Oh, the signs? Yeah. So this is the way that this is read. A union B is the set of all x such that x is in A or x is in B. So that would be the English way of reading this out loud. These symbols are just kind of a shorthand. And if you're, excuse me, describing certain sets, it might save you some time or space to write it this way. Oh, I see another question. Can you go over what a proper subset is? Right, so a proper or a strict subset, you can call it a proper subset or a strict subset, just 2 words for the same thing. This is akin to being strictly less than. So if A is a proper subset of omega, it means that for elements that are in A, they are also in omega. But there's elements in omega that are not in A. Then A is a proper subset. It is strictly less than. Whereas B here, this is a subset of omega, but it is not a strict subset, i.e., in this case, B is equal to omega. Okay. Okay, so that is a union. actually going to want to make this a bit smaller. Whatever. Okay, so the intersection is written this way: A intersect B, and this is equal to all x such that x is in A and x is in B. Pictorially, if that's A and B, then the intersection are those elements that A and B have in common. Oh, let me give a quick example here. So for example, if we have the set 1 and 2, and we union that set with the set 4, that will produce the set 1, 2, 4. That's an example of a union. Of an intersection, say 1, 2, 3, 4, intersect 3, 4, 5, 6. The elements that they have in common are elements 3 and 4. Okay. Now the set difference. Let me move this up a little bit. All right, so the set difference, for example, B minus A or A minus B. This is the set of all x such that x is in A and x is not in B. So if this is A and B, A minus B would be these. Right? Only those elements in A that are not in B. That is a set difference. As an example, if we have the set 1, 2, 3, 4 minus 1 and 3, then we would get the set 2 and 4. One thing about these three, and only these three, these work on the same kind of tuple. That is a schema. Which are the names and types of the columns in a relation. Okay, so in a relation, again, it's like a table. There's the, for example, name, SSN, age, I don't know, lot. There's the names of the columns. So each of these are going to have a name. And then they also have a type. So this is of type string, this is of type int, age of type int, and lot is also an int, let's say. And so, for example, you could have John with his social security number and age and lot. Mary, whatever. This is the schema. And these are rows or tuples, or entries. Okay. So the same kind of tuple means that all of the types are the same. The schema of a relation is the name and type of each column. So when I say that they work on the same kind of tuple, that is to say, if we have A with these columns and B also with the same columns, and A union B could work like this. So all of the rows are, this is concatenated row-wise. Okay, so you're taking this part A and putting it here, and then you're taking this part B and putting it on the bottom. For example, that would be one way to do a union operation. And this, you can do this because both of these are the same. If you had the letter C here instead of B, for example, then how do you union? Like, there's no real way to do a union with between these two relations. So for these relations, for these operations, all of these work on the same kind of tuple. Okay. Any questions about any of this so far?
Professor, I kind of fail to understand how you are relating these to tables. I would assume that if we're joining tables, we're joining them by column and not by rows.
Okay. I think you might be using join in a different way. We'll talk about joins. That will be the last. Actually, we'll talk about just the natural join. And so in that sense, if you join tables together, it's not row-wise like this. It is more column-wise. Just as a quick heads up, for this class, we are not going to be using joins. Or anytime we want to do a join, we're going to be doing it with lower level operators. So I'm going to show what a natural join is and how to recreate, how to do everything that that's doing using more basic operators. I'll get to that in a minute. But here, what I mean is if I had these two tables, maybe these are the boys. That's the boys table, and then we have the girls table, where there's Jane and Amy and Margaret. And I don't know. Okay, now if we wanted a table of the boys and the girls, then this would be a union. So the boys and girls table, we can construct this by unioning these two tables together. So we'd have name, age, and now in this relation, there would be John and Bob and Jane and Amy and Margaret of age 18, 17, 20, 19, and 19. So it's in this sense, I'm sorry if I use the word join, but this is an example of when you'd have different relations and they need to be of the same kind so that you can construct a larger relation. That would be unioning them. That's adding two together. So this is like addition in a
Right.
sense.
I misunderstood what was happening. Thank you.
Okay, yeah. Okay, yeah. So this is called algebra, right? I mean, you're familiar with algebra, 1 plus 2, that's 3. 3 minus 1 is 2. 2 times 6 is 12. 12 divided by 3 is 4, right? This is algebra. Algebra with, algebraic numbers, with numbers. And it has certain operations. There's a plus operation, there's a minus operation, there's a multiply, there's a divide. There's different operations in algebra with numbers. This is algebra with relations. And so that's what we're going over now, are like, what are these operators? And what do they mean when you're not dealing with numbers, but you're dealing with sets? And for example, addition, with sets, this symbol doesn't exist, the plus. So you can't say, John plus Paul with sets. The plus doesn't mean anything. But there is a union. You can say John union Paul. And that will combine the two together. John and Paul. So in effect, instead of the plus sign with sets, there's a union sign. That's sort of the addition operator. There is a subtraction operator. That's the set difference. Let me go back up to that. So this union is akin to the plus when you're dealing with numbers. The minus we have, and it works like how you might expect. If you have a set of things and you subtract things out of it, you're just removing those elements. There's another one, this intersection, and that's sort of special for sets. There's not really an intersection operator when you're dealing with numbers, because numbers are like finite things, where sets are collections of things. So this intersection, that's sort of a unique algebraic operator with sets. Okay, but that's why this is algebra. Okay, I'm just teaching you what the symbols are. Those are the operations that you can do. Okay, this next one is probably the most complicated. This is called the cross product. First of all, I'm curious, does anybody here already know how to multiply two sets together? Like if we had the set A as John, Paul, and Mary, and B is the set John and Paul. What is this? Does anybody know?
Like John times John and then John times Paul. And then since there's another John times Paul, you don't have to do the Paul to John again.
Okay. Yeah, sorry, your mic is a little scratchy, but start saying that again.
So would it be John times John?
Okay. So you're saying John and John. Okay. And?
And then John times Paul.
Okay, and then John times Paul, right?
And then since there's a Paul and John already, you would just like leave it.
No, that part not quite right.
So you would have to do Paul and John again?
Yep. Mm-hmm.
And then you do Paul and Paul.
Mm-hmm. Perfect. Wonderful, thanks. Yeah, so this is the cross product. This is all possible pairings. Okay, so between two sets, if you have sets A and B, the cross product of them are all possible pairings between elements of A and elements of B. So what we just did is we took this is A times B, right? Oh, here, A times B. So we take each element in A and pair it with each element in B. So there's the first element in A. It's paired with John, and it's paired with Paul. Those are those first two elements. Keep in mind, again, this is one element. Okay, so that's the first element. This is the second element, John, Paul. All right? And then you go and do the next pairings. So here's the next pairing, Paul and Paul. That's the second row here, Paul, John, Paul, Paul. And then Mary, John, and Mary, Paul. There's Mary, John, and Mary, Paul. Okay. Now, there's some subtleties here that are worth noting. But first, I want to say that well, I want to ask, do you think that this is true? Is B times A, does that have to be equal to A times B? Anybody? Aren't they the same? Yeah, that's the question. And yeah, so it doesn't always work like this. It depends, but in this case, yes, it works just like the multiplication of numbers, where if you say 2 times 3, then that might correspond to adding 2 to itself 3 times, which is the same as 3 times 2, which is 3 plus 3. Right? Like these, whatever, it doesn't matter which order you put them in, they're going to be equal. In this case, they are also equal, but that shows in some subtlety. So, yeah, Ariel, because you mentioned this, can you help me write down what this is? B times A?
Yeah. So would it be John, John, Paul, and then John, Mary? And then Paul, John, Paul, Paul, and Paul, Mary?
Excellent, thanks. Okay, so there's the set B times A. And if we want to know if A times B equals B times A, let's look through them. So here we have John, John. There's John, John. There's John, Paul. We have John, Paul. Paul, John. We have Paul, John. Paul, Paul. There's Paul, Paul. And now these two, Mary, John. Well, we have John, Mary. And here we have Paul, Mary, and here Mary, Paul. So let me switch the color here. Here is Mary, John, and this is John, Mary. And so here, these are considered the same. The same thing with these, Mary, Paul, and Paul, Mary. These should also be considered the same. Despite that, note that this Paul, John, and this John, Paul are not equal. So I can't really say that order doesn't matter, because sometimes it does matter. But between sets, order doesn't necessarily matter. Okay, so that's what I mean, like there's a little bit of subtlety. The right thing to always do if you're doing cross products is to find every possible pairing. And it doesn't matter which set you start with. Choose one, find all possible pairs. By the way, for B times A, we took the first element of B and then paired it with everything in A. And then we took the second element of B and paired it with everything in A. So one is you go through A, and for each element of A, you find all the pairs, go to the next element of A, find all the pairs. You could also start with B, find all the pairs, go to the next element in B, find all pairs. It doesn't matter which you choose. They might look a little different, but they're the same. Okay. What else do I want to say here? Let's see. So let me make that a bit smaller. Okay. So that's the way that a cross product works. And one thing I want to point out is if you have, for example, a relation A with these column types and a B with these column types, then A times B is going to have all of the columns of A and all of the columns of B. And this is probably going to have a lot more rows. So up above here, with these three operations, everything can be considered being done row-wise. Here, when we set multiply, in all cases, the width of the table is going to expand. That is also true if A and B are of the same type. That doesn't matter. A, B, C. If these were of the same type, then this table would just get a little wider. And there'd be ABC and ABC, be repeated. Okay, so multiplication always results in expanding the width of the table. Okay. There's a question. What is the size of A times B? Let me pick out, how about Ferna?
Hey, how are you?
Yeah, doing okay.
So I'm guessing 6.
6, okay. Why 6?
By the table that you drew, but I actually had a question.
Mhm.
Since they're getting multiplied, how come there are no sets like before, like AA and BB and CC, stuff like that? So wouldn't it be like maybe 9? Or
Wouldn't it be 9? Oh, okay. Okay, I'll answer that in just a minute.
yeah.
Yes, you are correct that in this case A times B is 6. The reason for that is because the size of A is 3 and the size of B is 2. So this is the size of A times the size of B. So you can always tell ahead of time how big the cross product is going to be, how many elements are going to be in the set. If A is a set of 3 elements and B is a set of 2 elements, then cross multiplying them will give you a set with 6 elements. Okay,
Wait,
now
how
for
come
this.
how come B is 2, Professor? Sorry.
Oh, sure. B here. B has John and Paul.
Oh, okay. I was
So
looking at the
so
table on the right. Okay,
okay.
makes sense.
Oh yeah. Yeah. Sorry. This table here, that's B times A. This is the table A times B. Okay. Yeah. So I'll try to be quick about this, and if you guys have something else to do, you're free to. Oh wait, no. We go to 120. Perfect. Okay. Good. We still have time. All right. So to the second question, let's be concrete. Name, age. We'll do this. Boys and girls again. Name, age. All right. Let's say here we have John and Paul, 18, 17, and Mary and Amy, 17 and 18. Anybody want to help me fill out this table? What's boys times girls?
So would it be 4?
Would it be 4? Like the number 4? What is 4?
Oh, no, I meant like 4 elements, or I guess it'd be
Okay.
John and Mary, John and Amy, and then Paul and Amy, Paul and Mary.
Well, first of all, how many columns do we have? How many
2.
columns? 2.
Oh, 4.
4. Um, okay, so those are our 4 columns. Okay. And what's the first row? What's the first element here?
I'm guessing one like a boy girl combination. I'm not really sure.
Okay, yeah. Well, it's all possible pairings. So you take the first row of boys and pair it with each of the rows of girls. So what would the first row look like?
So John and Mary, John and Amy.
Yeah, so John, who's 18, gets paired with Mary, who's also who's 17. And then John, who's 18, gets paired with Amy, who's also 18. Okay?
Hmm.
And then?
So then Paul 17, Mary 17, and then Paul 17, Amy 18.
Yeah, perfect. Perfect. Very good. Yeah. So it's in this way that, I mean, even if these are of the same type, the result is going to be wider. Because this name column is different than this name column. They have the same label, but they're sort of two different columns. This is the name column that came from the boys table, and that's the name column that came from the girls table. And that's how cross multiplication works. These tables can get very, very big. For example, if A is of size 1 million, and B is also of size 1 million, if the size of A is 10 to the 6th and the size of B is 10 to the 6th, then cross multiplying these two together is going to be very big. It's going to be 10 to the 12th. So cross multiplication is a very expensive operation to do. But sometimes it's unavoidable. Like, yeah, you got to pair things together. So, okay. Note. Okay. So this is probably one of the most complicated operations, the cross product. The union, the intersection, the set difference are sort of straightforward. The cross product takes a little bit more work. I apologize for the mess on the screen, but oh, why does B have ABC? Oh, I'm assuming you're asking about here. I was giving an example about how even if tables A and B have the same type, the result of a cross multiplication will still be a concatenation column-wise of their types. Okay. Oh. So no matter what, this is A's schema, and then this is B's schema. All right. So the next operation is called projection. And for the next couple of these operations, we're going to be using Greek letters for them. So here we use pi for a projection because pi is the Greek letter P. P for pi, or pi for P. So this operation turns many coordinates or dimensions or columns to few. Okay, so here the word coordinate, the word dimension, and the name column are all the same things. So for the boys times girls table, I can say that that has 4 coordinates. Name, age, name, age. Those are the 4 coordinates. It also is of dimension 4. The first dimension is this name column. The second dimension is this age column. And so I might go back and forth between using the words coordinates, dimensions, and columns, but they're all referring to the same thing. Okay. I'm sorry, just a moment, guys. Okay, sorry about that, guys. All right, so projection. This is turning many coordinates into few. So what I mean by that is if you have a relation A, and this has a certain schema, then through a projection, you could get rid of the B column. So this word projection is something that's used in linear algebra, also physics, where if you have a vector, maybe this is a vector, I don't know, 2, 2. This is a vector. And in the x coordinate, you want to know how much of this vector 2, 2 is due to the x direction. So if we were to write this vector as 2 vectors, one in the x direction plus one in the y direction, then what would these 2 vectors be? And you could do this by shining a flashlight on the vector from above and see the length of its shadow on the x dimension. In this case, this would be, I guess, 2 root. No, that's not right. Whatever. I'll say if this is root 2 and root 2, then that could be 1. So then the x direction vector would be this, and if you wanted to know the y vector, or the y component of this vector, then you just move your flashlight and shine it going in this direction and see how long the shadow is, or the projection of the shadow on the y direction. That would also be 1. So here. Yeah, fine. I'm sorry. No, that would be, yeah, if you didn't know what these were. This would still be 1, 1, actually. Whatever. This is just explaining where the term projection comes from. You have something, in this case, the tuple, or the row, let's say John, who's 18, in lot 2, this could be considered a vector of dimension 3. It has a name dimension, an age dimension, and a lot dimension. And maybe after projecting, maybe after projecting this vector, we get only the name back. So that's why it's called a projection. The number of dimensions always decreases. And yeah. So the reason that we'll use projection is because oftentimes a relation will have information you don't really care about. So it acts like a filter. You can just get rid of those columns that aren't important to you. As an example, I could make a projection to keep the first coordinate. And this is a function. So we'll put its input in brackets, or in parentheses. And the input for this is a set. Okay, let's say that this is a set of 4 things, 4 tuples. Then the projection would keep the first coordinate of this. And so this will return a set. And here, that has the first coordinate 1. So we would keep 1. Here, after projecting, we'd only keep the first coordinate 2. Here, we project, and we get the number 1 again. But remember, we don't need repeats in sets. So 1 is already in the set. It doesn't need to be added again. So I guess we have that counted. And then here we'd have the number 3. Okay, so that's a projection. Pause for questions. Oh, sorry. No questions? Can I explain that graph again? This in red, the projection one. Yeah, in red, is that what you're calling the graph? Okay, yeah. So it's just a little diagram to help you remember, I guess. So what this means is if you took if you have some relation A, after you project it, then you'll get something with, for example, filtered columns, A and C. Yes. If we have John, who's 19, who parks in lot 3, Sam, who's 18, who parks in lot 2, and Jerry, who's 18 and parks in lot 3. This could be a relation. I don't know, employees. Now we could project this, say, name and age. And if we give this relation as input to the projection, then the result could just be name and age. John, Sam, Jerry, 19, 18, 18. So we've just gotten rid of the lot column. That's what a projection would do. So, I don't know, this here is just a little bit more abstract. Great. Okay. The next one is select. And this is using the Greek letter sigma. This is not an O. It is not the number 6. This is the lowercase sigma. Okay, it looks like an O with a little hook on it. Just in case you're wondering, a capital letter is that sigma. You might recognize that from other math classes, but for whatever reason, they chose the lowercase letters. But it's sigma because it starts with an S, because it's a select operation. And this outputs a subset. Keep the tuple or not. Keep the tuple. Keep the entry. Keep the row. Same thing. Okay. I don't know. Here, if you have some schema, after putting it through a select, you'll get the same schema back, but with fewer rows. So maybe we keep that, we keep that, we keep that, we keep that, and we don't keep these. So these rows get deleted. All right, let's see an example with symbols. So if we want to select when the second coordinate is even of this set, so same set as above, 4 elements, and we keep it. So we're selecting only those elements from the set where the second coordinate is even. So that one's even, that one's even, this one is not even, this one is not even. So this would return the set with elements 1, 2, and 3, 4. Okay, Oh, I'm sorry. There's one more that's really quick. Let me do that really fast. This one's really not that interesting, but necessary. This is the rename. So this is just a way to rename a row. Speaking of which, that's the symbol for it, and that is the Greek lowercase r pronounced row. So I don't know if you have some relation A with A and B and C, then after renaming, it could be the same thing except with columns alpha, beta, and gamma. Just renames a row. So row, I don't know, SSN to employee SSN with some relation R. Maybe R originally is SSN. It's just a list of SSNs. Performing a row on this would return the relation, except now it's called employee SSN. Do age as well. Okay, so that one's a pretty simple operation. The rename just renames a column. That's all. Okay, so let's go through these again really quickly. These are the seven. These are the seven basic operations that you can do anything in relational algebra with. The first is the first three I'll group together. That's the union, the intersection, and the set difference. I'm grouping these together because each of these work on the same kind of tuple. So both of the tables have to have the same number, type, and name of columns. So the union works like addition, subtraction. We have here intersection is something unique to sets. Here we have multiplication. Like multiplying numbers, it doesn't matter the order that you multiply in, but the procedure for multiplying is different. The procedure is finding all possible pairings. That's what a cross multiplication is. Okay, then we have a projection, which is a way to kind of delete columns. We have a select, which is a way to not delete columns, but to delete rows. And then rename, that's just renaming a column. That's it. Let me pause for questions.
Hey, Professor, I have a quick question. So between 5 and 6, can you explain like a little more like the difference between them? Because it's just going from many to few, or
Yeah,
never mind. It just picks the tuple itself, right?
yeah. So 5, you can think about that as deleting an entire column. So here in red, if we had some relation with columns A, B, and C, you could project it and delete the entire column B. So a project is like a column delete. You delete an entire column. 6 is a select, and that's where you delete rows. So not columns, but rows. You're deleting tuples. So a tuple is a row of the relation.
Okay,
So
makes sense.
Yeah. We are going to. Okay. Well, first of all, I want to make sure if there's any more questions about these operations. No. Okay. We're doing pretty good on time, I think. So I'm going to teach you this now, and you can refer to it later or not. But after today, this won't be, so useful. And by the way, again, you can go through the book. This is all in the beginning chapters. No, I think this is maybe chapter 2 or 3 now, where it talks about relational algebra. I'm teaching the same notation and everything as is in this book. This book will also has some more operations. One of them being this one, the natural join. There's some other types of joins. I'm only going to be talking about the natural join in this class. And I will tell you that all of the joins are redundant. You can do all of these join operations using the above 7. I'm going to demonstrate that with the natural join. And for this class, I want you to do the long thing. Okay, so if you write join, or if you do if you use the join word, I will deduct points. The reason for this is because I've found that a lot of students think that join kind of sort of works like magic, and then they don't really understand what they're doing when they try to join things together, especially with more complicated queries. So for this class, we're going to go the long way. It's not that much worse, to be honest, but there's 2 benefits to that. One, I believe that this will help you avoid making mistakes in the future with join. I'm not saying don't ever use join. I'm saying for this class, don't use join. As soon as you graduate, great. Now I think that you should be comfortable enough to use it appropriately. So that's one reason. The other reason is because it's not just that you can do these things another way. It's that that's what's actually happening. When you do a join operation, there's stuff under the hood that's happening. It's not just one operation, it's actually a sequence of operations. And that's what I'll be teaching, and that's what we'll be going through in this class, is what are those sequences of operations. I think that will also help you appreciate when to use joins and how to use them. So without further ado, let me first tell you what a natural join is, and then another way to reproduce it. So now this isn't using a Greek letter. It uses this symbol, which is a bow tie. Bow tie. Okay. And what this does is it selects or filters tuples with a common attribute. Okay, let's see a quick example of that. if we have some relation A with, I don't know, name, age, and some B, name, OS. Here we have John, both of them. He's still 18, and he runs a Mac. And then we have Amy, who's 19, and I don't know, here's Susan, and she uses Linux because she's a cool programmer person. Okay. Now, if we do A natural join B, this does a few things. First, it will combine these tables horizontally via their attributes. So this will have a name column and an age column. And instead of having a name and an OS column, the natural join recognizes that these two are the same thing, and so it will get rid of that. It'll get rid of the repeated one. Sorry, this is age. So this is going to be the common attribute, the name. And inside this table will be those entries that share a common name attribute. So John appears in table A. John also appears in table B. So this will have John. We know his age from the first table, and we know his OS from the second table. And that's it. That's the only entry. Amy does not appear in table B, so she's not in the natural join. Similarly, Susan is not in table A, and so she doesn't appear in the natural join either. Only John appears in both tables. So it's a way to kind of merge tables together, only keeping those elements that appear in the tables that you're merging. Something like that. Okay, are there any questions about the operation? Like, given these relations, what would a natural join look like? No. Okay, well, then let's wrap up class with showing another way of doing it. Actually, the way that a natural join actually happens. It's not the word that you use, but if you looked at the code behind it, you call a natural join, it will call other functions of these previous 7. So let me, I guess, pick out on random people. How about Mark?
Hello, Professor.
Hey.
How's it going?
Oh. Very good. Okay. Besides the natural, okay, so what we want to do is we want to be able to take these two as input and go through sort of maybe a multi-step process to arrive at this same relation. So what is one way to combine two tables together, to combine two relations together that we've talked about?
Using the operations that we just discussed in class, or Is it like an intersection or just
No need for intersection.
no need? I'm not too sure, Professor.
Okay. Let's see. Let's do a cross multiply.
Okay.
So if we cross multiply A and B, so if we do A times B, what does that relation look like?
So in terms of just like, yeah, we'll just look at John and we would do like all possible pairings.
Okay.
So it would be like John, Susan, John, Amy, Susan, Amy, John.
Okay. Is that all that's in the relation?
And I guess like the tuples would be name and
Mm-hmm.
name, age, and then that would be like the A schema, and then the B schema would be name and OS. But since name is already there, we would just I'll get there. Yeah.
Okay. And so then we'd also need their ages, right?
Yeah.
And their OSs. Very good. Okay, thanks. How about, okay, so one thing that we'll also do is instead of just doing A times B, we're going to rename name to name2, B. And so we're actually going to be multiplying A by the result of this rename. So that way we'll have one column name and another column name2. Okay, so there's a cross multiply and a rename. And I actually think, oh yeah, there's not so much left. Okay. Yeah, I'd rather go through this with you guys. Yeah, let's finish this up at the beginning of next class. I don't want to keep you over, and I don't want to just throw out the answer. I'd like to go through this with you. In fact, maybe you can consider this your homework. How can you get here by using these other operations? I'll tell you which ones they are. It will involve a cross multiplication, a rename, a select, and a project. With these 4 operations, you can do a natural join. So try it out, and I'll see you guys on Friday.